entropy in thermodynamic systems. In this session, we will explore the fundamental concepts of entropy from both microscopic and macroscopic perspectives. Our outline includes the microscopic definition of entropy and Boltzmann's famous equation. We will then examine how to calculate entropy changes in ideal gases and look at the macroscopic definition used in practical thermodynamics. Finally, we will discuss the relationship between entropy and the second law of thermodynamics to understand why certain processes in the universe only happen in one direction. Entropy is a concept deeply rooted in the ideas of uncertainty, the number of available choices, and probability. When we analyze macroscopic systems containing a vast number of particles, we must use statistical methods. A key principle here is that macrostates associated with a larger number of microstates have a higher probability of occurring and, therefore, possess higher entropy. In terms of measurement, the units of entropy are joules per Kelvin, which are the same units used for Boltzmann's constant. Ludwig Boltzmann established the link between entropy and the number of microstates, represented by the letter W, during the 1870s. The currently accepted form of his equation states that entropy equals Boltzmann's constant times the natural log of the number of microstates. Here, W represents the number of different ways or arrangements of achieving a specific macrostate. When a system undergoes a change, the change in entropy is calculated as Boltzmann's constant times the natural log of the ratio of the final number of microstates to the initial number of microstates. To understand the spatial entropy of an ideal gas, imagine n molecules in a volume, V, where each molecule occupies a tiny microscopic volume. The number of ways to place a single molecule is the total volume divided by that microscopic volume. For n molecules, the total number of ways, W, is that ratio raised to the power of n. Using Boltzmann's equation, we find that the spatial portion of entropy equals the number of molecules times Boltzmann's constant times the natural log of the volume ratio. This can also be expressed using moles and the gas constant as entropy equals the number of moles times the gas constant times the natural log of the volume divided by the microscopic volume. Entropy is not just about where particles are located, it also has a temperature-dependent portion. If we consider a process at a constant volume, where the temperature increases, our spatial entropy equation suggests no change because the volume remains the same. However, as the temperature rises, molecules distribute themselves into higher available quantized energy states. This increased spread in energy distribution leads to greater uncertainty and higher entropy, even if the physical space the gas occupies does not change. While the microscopic approach is theoretically sound, evaluating the number of microstates is extremely difficult for macroscopic systems with roughly 10 to the 23rd power particles. A more practical macroscopic definition uses heat and absolute temperature. A change in entropy is defined as the integral of the reversible heat transfer divided by the absolute temperature. It is important to remember that entropy is a state variable. This means the change in entropy between two states depends only on those endpoints and is entirely independent of the path taken to get there. Let us look at a quick quiz regarding path comparison on a pressure-volume diagram. An ideal gas moves from an initial temperature to a higher final temperature via two different reversible paths. Path A occurs at constant pressure, while path B occurs at constant volume. Although entropy is a state variable, we must be careful here because the final state for path A and the final state for path B are actually different points on the final temperature isotherm. Because they end at different points, the total change in entropy for each path will not be the same. We can calculate the change in entropy during a phase change, such as melting. Consider a substance of mass, m, with a latent heat of fusion melting at a constant melting temperature. Since melting is an isothermal process, the temperature stays the same and can be moved outside our integral. The total heat added is the mass times the latent heat of fusion. Therefore, the resulting entropy change is the mass times the latent heat of fusion divided by the melting temperature. This value is positive because energy is being added to the substance. Now consider the entropy changes within a Carnot cycle operating between a hot reservoir and a cold reservoir. During the isothermal expansion, the entropy change is the heat absorbed from the hot reservoir divided by the hot temperature. During isothermal compression, the entropy change is negative because heat is expelled. For the two adiabatic processes, the entropy change is zero because no heat is transferred, and the processes are reversible. When we sum these up for a full cycle, the ratio of heat to temperature for the hot and cold parts cancels out, resulting in a total entropy change of zero for the complete Carnot cycle. In an adiabatic free expansion, a gas expands irreversibly from an initial volume to a final volume into a vacuum. Although no heat is transferred during this irreversible process, we cannot simply say the entropy change is zero. Instead, we must find a reversible path that connects the same two states, such as a reversible isothermal expansion. Using this equivalent path, the entropy change is the number of moles times the gas constant times the natural log of the final volume divided by the initial volume. Since the final volume is larger than the initial volume, the entropy change is positive. Thermal conduction provides another clear example of entropy change. Imagine energy Q flowing from a hot reservoir to a cold reservoir. The cold reservoir gains entropy equal to the heat divided by the cold temperature, while the hot reservoir loses entropy equal to the heat divided by the hot temperature. The total entropy change of the system is the heat times the quantity of 1 over the cold temperature minus 1 over the hot temperature. Since the hot temperature is always greater than the cold temperature, the total entropy change is always positive. Let us compare the microscopic and macroscopic approaches using a gas that expands to 4 times its initial volume. Macroscopically, we calculate the change as the number of moles times the gas constant times the natural log of 4. Microscopically, we look at the ratio of the final number of ways to the initial number of ways by taking the natural log of this ratio and multiplying by Boltzmann's constant. The math simplifies to the exact same result. This confirms that both the statistical look at particle arrangements and the thermodynamic look at bulk properties yield the same conclusion about entropy. This slide illustrates the path independence of entropy using a pressure-volume graph. We can calculate the change in entropy between two states using any reversible path. For example, consider a two-step process where we first have an adiabatic expansion from state A to state B, followed by heating at a constant volume from state B to state C. In the first step, the entropy change is zero because it is an adiabatic reversible process. In the second step, the entropy change involves the natural log of the temperature ratio. By substituting the relationship between temperature and volume for an adiabatic process, the result leads us right back to the same entropy change we found previously. The second law of thermodynamics tells us that the universe constantly moves toward macrostates with higher probability. This movement corresponds to the continuous spreading of energy across space and time. According to the entropy statement of the second law, the entropy of the universe increases in all real processes. Real-world processes are irreversible and naturally lead to a more equitable or uniform distribution of energy. While the entropy of a small system might decrease, it must be balanced by a larger increase in the entropy of the surroundings. To summarize, entropy is a fundamental measure of the number of microstates associated with a specific macrostate. Boltzmann defined this relationship using the natural log of the number of microstates. In the world of thermodynamics, we typically calculate these changes by integrating the ratio of reversible heat transfer to absolute temperature. Because entropy is a state variable, its change is independent of the path taken. Ultimately, the second law dictates that for any real process, the total entropy of the universe must always increase. We conclude with 2 review questions to test your understanding. First, consider why we must use a reversible path to calculate the entropy change for an irreversible process like free expansion, even when the actual process is not reversible. Second, think about thermal conduction between 2 reservoirs. Why does the total entropy of the entire system increase, even though one of the reservoirs is losing energy and therefore losing entropy? Reflecting on these will help solidify the connection between energy spreading and the mathematical definitions we have covered.